So in my talk, I mentioned that the vast majority of the major meteor showers were connected with known periodic comets, short period or long period comets. But there is one major meteor shower that is the exception, and that is the Geminids of December, in that it is not connected with an existing comet, but with possibly an extinct comet. Studies of this particular stream and the parent body have been going on for a long time, and who better to tell us about this than one of the meteor section's leading luminaries. Alex Pratt, your next speaker, is an expert in many areas of astronomy, not just meteors, but occultations and many other fields as well. And I'm very pleased that he was awarded the Walter Goodacre Medal and Gift last year for major contributions to amateur astronomy. It is the association's highest award. He has made a special study of the Geminid meteor shower over many, many years, and here to talk about the Geminids and their parents' body, please welcome Alex Pratt.
Thank you. Thank you, John. I think you've mistaken me for someone else, but never mind. But I'll try to keep to time, but I usually put too much information into the talks. So we'll go at a moderate pace. But just say that a few years ago, I was at a European astronomy meeting in Barcelona, and their technique was the chair. When you had 5 minutes to go, they showed a yellow card, and then when it was time to finish your talk, you got a red card. So let's hope we're not doing that today. So I'll try the keyboard rather than the gizmo, because I usually end up... So we have to put a warning out first, because meteoroids are harmed by our studies. So we have to put a Solar System Humane Society mention in there. But as John mentioned earlier, the Geminids are one of the best showers of the year. We have the Quadrantids early January, the beloved Perseids nicely through the summer, and the cold winter nights, the Geminids, and they peak around December 14. John also showed the Global Meteor Network's strip chart there. Geminids peaking very similar to the Perseid level, but you'll see in the bottom line, solar longitude 262. That's the date which we would see the Geminid maximum, and it's what meteor workers use rather than the calendar and leap years, analogous to variable stars observers who use Julian date. So, what do we normally see of the activity profile of Geminids? On the top is Global Meteor Network's nice video data graph. See a steady, clear build up to maximum. Often you can have two peaks there, probably a pre-peak before the main peak, because some researchers think there could be two streams involved in this. It doesn't always display this activity. The graph below is the IMO's video data. Not as much coverage, but similar profile. They also have quite a few observers doing visual work, so that's the visual plot. Looks characteristic, similarly, with two dips and a drop at the end. That's notable with the Geminids. And many people say, who turned off the tap? Because we see a spectacular display, and then the next night, they've almost finished. What happened? We must be moving out of the stream, perhaps like driving through a rain shower, and suddenly, oh, it stopped, it's dry. So what I did was look at the BAA and IMO historical data that I could find of counts of Geminids and Perseids. So the false circles are the Geminid data, going back to the 1800s, and you'll see there to the right a general trend with very high zenithal hourly rate counts, 100, 150. 1990s and 1860s, is it? You can see the peaks of the outburst of the Perseids. But I would say that the early data in 1800s onwards for Geminids, people then were doing mnemonic chart plots to track the trails of meteors and perhaps radiants, and they didn't keep data on the counts, the hourly counts. So it's all very approximate data. Perhaps multiply that by 50% to get what might be a ZHR now. If you can't read that, I'll just mention that's a little note by Alexander Herschel, and he said in 1865, reporting that we had seen a radiant point near Castor on the 6th and 12th of December. This centre of radiation, which they marvellously called it then, radiation of meteors, was first observed by Mr. Gregg at Manchester from the 10th to the 11th, and also Professor Twining and Mr. Marsh in the United States. So they had done multiple observations and tracked that there was a point near Castor where these were radiating from. And also, William Denning, a bit later, he also commented that he had measured the radiant drift of the Lyrids and Geminids and proved that 1 degree per day motion because of the Earth's orbit does occur. And on the right, he's given an ephemeris for where the Gemini radiant is. How do the Geminids Perseids fit into the pantheon of meteor showers? So this is sorted in descending order of velocity where they hit the top of the atmosphere. And we're talking about really high-speed events. So the Perseids there, 59 kilometers per second, which means nothing to me. Equated is 130,000 miles per hour. Geminids, a mere 78,000 miles per hour. And I haven't said what the parent body is, because we know what it is, but we're going to tell the secret in a minute. For an equivalent measure, my SR-71 Blackbird, which I had a model of when I was a kid, that would shift at about 1 kilometer per second. So the Geminids coming in are 35 times faster than that reconnaissance plane. Likewise, when Apollo 10 came in, it was a third of the speed of a Geminid meteor. Looking at the mass data from Global Meteor Network over the last few years, if we take the data in the magnitude ranges, so this is absolute magnitude. It's the magnitude a meteor would have if it was 100 kilometers above the observer. It's like a standard normalizing procedure. And I think you can see that as we move to the right to the fainter meteors, the green column are Geminids, and they seem to be more proportionate than the Perseids. And then to the left, the Perseids are higher counts. And at top left, you see the mean magnitude from this video data. Geminid was about minus 0.3. The Perseids about a magnitude brighter. Pardon me. We can also look at the heights where we first see these meteors. How high up are they in the atmosphere? And the green band, Geminids, roughly 95K up. But the Perseids are faster, nearly twice as fast. So the kinetic energy they have, half mv squared, is much higher. So we see them at a higher altitude. The smudging scattered to the top left, pardon me, does not appear until a couple of years ago. So I wonder if that's something in with the data collection or atmospheric conditions changing. And conversely, where do we last see? Where do the meteors fade out? So from right to left, we're going in fainter meteors to the brighter ones on the left. And as we get to the brighter meteors, then if all meteoroids in a stream are traveling at the same velocity, then the brighter ones we'd expect will be the larger particles, causing brighter meteors. See, the Perseids seem to be limited to a ceiling of about 70K, and they burn out. That's it. but the Geminids are getting down to 50 or even 40K. It has been postulated that perhaps someday there might be a Geminid meteorite land, or at least there could be micrometeorites coming into the atmosphere. There's a nice paper by the UCL and a Norwegian researcher, thank you very much, looking into collecting rooftop debris and sorting it and analysing it, and they found 500 micrometeoroids, but they said almost all were chondrite asteroid material, not perhaps cometary. And at the very recent International Meteor Conference, I think it's a Dutch group, they gave a lovely talk on how to catch a falling star by checking your downfall pipe, etc. So I will put the links to those on the BAA forum because we have a thread discussing micrometeorites. The other nice thing we can extract from Global Meteor Network data is the meteoroid masses. So from the magnitude, they estimate the mass of a body. See if I can get the pointer to work. Yes, I've got, anyway, no, it's me. But don't worry, at the 0 magnitude point, I had it upside down. Thank you, John. 0 magnitude point, as we move up to get a 0 magnitude Geminid, then you've got, that is about 1/10 of a gram of material. But proportionately, if we go across to the left for a Perseid, it gives you, that would be not 0 mag, but probably between -1 and -2 because of their higher speed. And I think in general, you can see the graph is just shifted to the left between the two types of meteor. So there's a lot of different particles appearing in these meteor showers. And in the 1980s, our then Meteor Section Director, George Spalding, did an analysis grouping the different magnitude groups of meteors and seeing their activity profiles. And he showed that the fainter meteors appear to gather a bit earlier in the stream's arrival, around maximum. And then at the end of maximum, we've got the brighter ones. So it's particle sorting. It's caused by the Poynting-Robertson effect, which is on very tiny particles. They are absorbing solar radiation, and then they re-radiate it, and it causes a slight retardation in their orbits, so they spiral in to the sun over thousands of years. That's why John explained that the showers slowly get depleted of their smaller particles. We won't cover that slide in detail, but that's following up from George, and he took the masses of the bodies, and he showed this is a mass index, but what it means is before Geminid maximum, he's got an increasing value here. That means there's proportionately more small particles in the data set. And as we get to the visual peak, you've then got, it goes the other way, and then some of the larger particles, the brighter particles, are dominating. So that was 1980s. A few years ago, a Japanese researcher wrote into WGN, IMO's journal. He repeated it using thousands and thousands of IMO's visual data. I won't show all of these graphs, but he said, yes, you compare the magnitude 0, the peak occurs about here, just beyond 262, but the very bright meteors, you can see they're shifted across. They're occurring later. He produced a linear relationship of all of those magnitude groups, and all it does is it confirms George's work. He listed his comparison with radar work, and at the end, is crediting George Spalding and the Japanese worker with the latest visual data for tens of years got almost the same results. He also did a study of the population index. And in meteors, what that roughly means is we're seeing so many mag-1 meteors. We'd expect to see more mag-0, maybe more again mag-1 and more mag-2. So this compares the ratio between these magnitude groups. And what he was saying that yet again, before maximum, the fainter meteors dominate, then they get reduced, and then we get more of a proportion of the brighter ones. So yes, more confirmation of particle sorting in the Geminids. So the secret, we put question marks at the front with the Python, what is the parent, what is the comet, or otherwise, that creates the Geminids. And I think, pardon me, I think many of you know the answer, but talking to our friend today who worked on the IRAS astronomical satellite, and launched in 1983, it detected many, many bodies in the solar system, but one of them was 1983 TB designation it was given. Later studies showed it was about 5 kilometers across, 3 miles across. Charles Cowell did astrometry of it, determined its orbit, confirmed where it was going, and also the esteemed Fred Whipple took the photographic meteor survey data where he'd worked out the orbits of the Geminid meteors, and he wrote an IAU circular saying, yes, it's a match for 1983 TB. We have found the parent. It's this asteroid, not a comet. And then a bit later, the official body, the IAU, then gives it a designation 3200 Python, and they named it after the sun god Helios. And there's a very good reason why they did that, because when you see NASA Horizon's plot of its orbit, at perihelion, it goes to 0.14 AU. That's well inside Mercury's orbit. And so you've got temperatures up to 750 C, and it must be causing thermal fracturing in the structure of this body. A comet would have volatiles. This must have all been boiled away. You would not have sublimation at these temperatures. You see it's quite an elongated orbit, eccentricity about 0.9, sweeps out to AU, orbits very quickly, only 1.4 years. So it's like in fast forward, not like a comet taking 130 years. It's high speed as this body. And because it overlaps Earth's orbit, it's categorized as Apollo type, potentially hazardous. But we're okay, they tell us, for at least 400 years. NEODIS lists Python close approaches. Thankfully not too many come near, and in 2017 we had December. That was one of the best for several decades. This was a schematic of it. So Python was coming back round towards the sun. The Earth was passing nearby. So as far as we're concerned, it's a long way off, but 25 lunar distances away. It was then about mag 10.5 over those few nights, moving at 39 arcsecs per minute. So this is one of my videos from it. So you can see this pair of stars here. If you look at the top one of the pair, it is slowly moving to the right, because I do video astrometry of asteroids and some of the brighter comets. So that is Python at mag 10.5, 10.8, ambling through the skies, and that's a half-degree field across the diagonal. As well as many amateurs monitoring the body, professionals all over the world, including the esteemed, late-lamented Arecibo radio telescope, took these radar echo images. They put in an animation. Looks like a like a ghostly creature, doesn't it? But because the radio telescope and other professional work had highly tied down the orbit of Phaethon for us very accurately to within hundreds of meters, those of us who do occultation work, where an asteroid, we have good data on the orbits of asteroids, we have the excellent Gaia star catalogue, so we have predictions of the asteroid blinks out a star for 1 second or 2, 3, 4 seconds. If a series of observers can record disappearance, reappearance data, in a way, it's a reverse of a solar eclipse, where the star is causing the shadow of the asteroid to appear on the Earth. And we can get chords across the body. We get high-quality astrometry because the position at middle of the occultation is the midpoint of the Gaia star. Ra index to whatever it is, micro arc seconds, or it's incredible what it has. So Dave Harold, our occultation guru, who develops the marvelous occult software we all use, he worked with NASA JPL to do extra prediction updates, because you're trying to get an event where the shadow is 5 kilometers across on the Earth, and they added in extra work for the gravitational bending, the relativistic change of the light path coming through the solar system, perhaps deflect Sun and Jupiter pulling on them. The Americans set up a big campaign to observe this. It's like a sky map looking to the sky, but these are like 40 or more American observers. This technique that they call picket fence, where they're hoping they'll get a hit, and luckily in the center here they did, and we can show the enlarged part. So the dashed lines are the uncertainty error bars on the timing, roughly elliptical, so we just fit a nominal ellipse to it. And you can see that we said that Phaethon was, my eyesight gets worse, but was it 5-point blob times 4.7 K across. And then the game was on then, because we could predict where the shadow tracks would be, and we could do more modeling of Phaethon. So the Japanese follow it, they're very keen on it. Dave updated the predictions for the topographical nature, because previously they were modeled on a uniform geoid spheroid of the Earth. But if you're in Colorado at 5,000 feet up, the track is actually displaced somewhat. And when you've got to be within a kilometre or more, these adaptations were done. The Japanese got lots of chords here. There's more measures of Phaethon. And we've also got shape models being developed as well with the professional team. So it's all helping the future research, which we'll come to in a minute with the space probe. John mentioned Yarkovsky and Yorp effects. Poynting-Robinson affects tiny particles, dragging them back into the sun. But if you imagine you've got a body here heated by the sun, and it's rotating, it will radiate heat as it's spinning round. And in the long term, there's a residual effect. It will either accelerate it slightly or retard it slightly. So the asteroid will slowly move into the sun or away from the sun, or it might arrive a bit early or a bit late in the position where you expected it. Dave Harold, David Dunham, USA. Don't worry about this table, but he catalogued all of the observations up to a few years ago with the radar, Gaia, the amateur occultations. And the key thing he's looking at is this value here, this number, and it's Phaethon's A2 transverse non-gravitational parameter. So, as we say, it's the pull or tug or the displacement in its orbit caused by this re-radiation of heat. And NASA Horizons keeps a record updating that. As we keep observing the occultations of Phaethon, that's Every few months, if we can get an event, we're revising it. And just to equip, really, if you watched 2010, the film Odyssey 2, the Russian scientist says to Hayward Floyd, check the orbit, because Discovery is moving in its next to Jupiter. It's not where you think it is. So, quick overview. What is Phaethon? Is it a comet? Or you see these references, it's a rock comet. So you think of it trashing hotel rooms or something. What is it doing? But they say it seems to brighten very briefly after it's been near perihelion. So we'd expect it to be giving off gas or dust. Or the Parker Solar Probe has monitored it, and it sees a very tenuous sodium gas tail coming off. So not particulates, but very, very fine. So that would not replenish the Geminid stream, but unlike a comet, which John explained, is laying down debris each time it's whizzing round. But we're thinking that this thermal fracturing is causing it to give off lots of particles which will maintain to some degree the Geminid stream. Professionals have done spectroscopy of it, and they categorize it as just another chondrite asteroid, so a main building block, one of the simpler asteroid forms. Modelers have said, well, we think it could be created by a violent event 2,000 or more years ago. So was it, there's also, not quite fantasy land, but there's ideas. Was it a sun-grazing comet that was captured? So is it now the comet nucleus that's still orbiting the sun in this close orbit, this very close pass? Is it more likely an asteroid which is fragmenting? Did it collide with another one and found itself there in that location? So if you check all the papers, you'll see lots of research papers going over all these ideas. It's a fast rotator in only 3.6 hours. And there's other minor bodies, which they call a Phaethon complex, which might be a similar family. So are we finding one or two more like these? Are they comet nuclei? Are they just asteroids which are giving off enough material to form a meteoroid stream? Asteroid Bennu, this was visited by OSIRIS-REx. They gave these beautiful images there. This is 500 meters across. Look at the size of some of those big particles. So does Phaethon look like that? We don't know. Another image that they've done, and you see it on the left, they've enhanced it, and there's all these tiny particles coming off. Imagine if you could get down to millimeter and smaller scale, what cloud will be around this? Is this analogous to Phaethon? So what we're waiting for is Destiny Plus. And it's a mission by JAXA, the Japanese Space Agency, and German Aerospace. The German team are doing the dust collection monitoring. Well, will not collect, but it will analyze dust. And with all these missions, there's an acronym. So Destiny Plus. So you can see a whole team has worked on that. Must mean demonstration and experiment of space technology for interplanetary voyage with Phaethon, flyby, and dust science. So that's one for the pub quiz. So we're just about finished now. Schematic of the Geminid meteor orbit, which we've got from video data. We know that, if you can see, perhaps you can see the Earth there, little blue dot. We sweep around anti-clockwise, and we meet the Geminid stream from the inside of the torus, the inside of the hula hoop. What's happening is perturbations by Jupiter, Venus, and the Earth are tugging the Geminoid stream away further out. But apparently we are going to be moving through denser parts of the stream. So anything in the next 100 years, 150 years, The ZHR we're now getting 100, 150, sometimes 200. The norm could be 200, 250. And with all that fragmentation, we occasionally get bursts of 100 or 200 ZHR over 1 hour or 2 hours, but could we get perhaps beautiful big fireballs coming in from these chunks? Who knows? So we'll complete that quick run through. As you see, it's a very dynamic meteoroid stream, and the meteor shower is evolving because we don't have a parent body going around 100 years. It's hurtling around every 1.4 years. What's going on with the fracturing, replenishing? Where will the ZHR go? What is this rock comet parent? What can we find out about that? What will Destiny Plus tell us? So whatever you do, please have a look out this December. The Geminids are going to be superbly placed. You might set up a video camera system like William, but the GGs are optional. And also you may want to try some visual work like in the good old days, and have a look on the BAA website for how to do visual watching and collect data in the useful manner. So I hope I've kept more or less to time, and we'll just say thank you for listening.
Do we have any questions for Alex? Yes. Stephen.
I must say I regard visual observation as a superior one, but anyway, above all of them. Given the torus of the stream you just mentioned, approximately when would the kind of peak ZHR be, and when would the Geminids finish? Because
the modelers were saying that they're expecting near year 2200 for the peak rates, but who knows if it could be like 2150. Then they say after that we will start to lose the Geminids. We'll move away. But like with all these things, it's just theoretical modelling, and we know that the true story is told by us going out and observing it visually or collecting data. But it does look as if next 100 years it's just going to get better and better. So in our lifetimes, we're in for a treat. We're not going to lose them. And I haven't seen any analysis proposal as to, well, what does that then do? Does it mean that it slowly reduces after another 100 years? Does it go on? We'll have to see. But you've seen that the width of it there, the Earth takes about 10 days to detect the Geminid stream. So we move about 1.5 million miles a day. So the stream that we see it is 15 million miles across. But it's only, as David Hughes used to say, it's only what we see on the spaceship Earth that we detect. So I think we'll be seeing the Geminids for a long time. The 100, 200 or 300 years. But how that tails off, that's other generations to see. So if you have video cameras or you enjoy doing visual work, then yeah, just and get out, because with visual work you will see the solar system in action. Video cameras are nice, but it's second-hand.
Going to outlive all of us. Thank you very much, Alex. Thank you for that.
I'm around for the rest of the day, so catch me if you've, like Dennis said, if I've got it all wrong, just come and see me.
Yeah. There'll be a tea break, so...